Okay, thank you for the introduction and welcome everyone. Today I want to present you our SPAD-based flash LIDAR line sensor with photon coincident for background rejection. This is the outline of my talk. First, a small introduction, what we are measuring and how it's working. And then I will explain our chip, the chip structure, the pixel design, and how the TDC is working. And at the end, some measurements and short summary. This is how we use direct time-of-flight measurement in our sensor. It means we have a laser source which is emitting short laser pulses. They are reflected by an object and go back to the sensor. And we are measuring the time from the emission of the light pulse till the detection of the first photon. And multiple of these times are collected in a histogram, and from this histogram, with a use of a proper software algorithm, we are determining the true time of flight, and from the time of flight, we can calculate the distance. So this is a micrograph of our chip. We have a 80-pixel line sensor, and the SPADs are located in the middle of the chip. Here in this version, we can see these bright dots are the SPADs of the chip. And as I said before, it's using for direct time-of-flight application. And the chip was fabricated in 0.35 micrometer high voltage CMOS process. And for detecting the photons, we are using single-photon avalanche diodes, SPADs. And because one application we are aiming is the automotive, and there we have very high background light, for example, the sun. And to reduce the influence of this background light, we are using photon coincidence detection. This means we only stop or start our TDC when in a given time, at least a given number of single events are detected. How this will work, I will explain in the next slide. For time measuring, we are using fully parallel DLL-based time-to-digital converter, so we can measure the time for all the pixels in parallel. And we are using 200 megahertz on-chip clock, and we have a resolution of 312.5 picoseconds, which is about 5 centimeters, and a full-scale range, so a maximum distance of about 200 meters. It's 1.28 microseconds. So this here is a screenshot of the layout from the pixel. So at the top, we can see the SPADs. We were using 4 SPADs with a size of 20 times 20 micrometers. And the pitch of the pixels is 100 micrometer. The height is 400. And we achieve, if we look only at this area here, a fill factor of 19%. Here we can see this block diagram of the sensor. So we have 4 SPADs, and each of the SPADs has its own active reset and quenching circuit. And this quenching circuit gives signal pulses each time a photon is detected, with a length equal to the death time, which is in our case about 20 nanoseconds. For the photon coincidence, we are using pulse shapers with adjustable widths. And this width corresponds to the coincidence time, so the time in which the given number of events has to occur to be classified as a coincidence event. These pulses are given to several logic circuits for different coincidence steps, so number of events to have a coincidence event. And since we are using 4 SPADs, we have circuits for 1 to 4 events. And by using a multiplex and select one of the outputs from these logic circuits, we can choose the coincidence step we want. And this output signal here is given to the TDC, which is built of a 8-bit curse counter for curse time measurement. It's just counting with our 200 megahertz clock. And a time interpolator to measure the time between the start signal and the next rising edge. For this, we are using a DLL in global level and delay our clock signal in 16 steps. And this 16 step, or the 16 phases, are frozen by the use of arbiters. And from the states of these clocks, we can calculate the actual time. And also to measure background light, as in the previous talk, we can also use our sensor in counting mode, so just counting the events which are delivered from this multiplexer here in our 8-bit counter. So this is how the TDC is working. So we have here a start and a stop signal, and when the start signal comes, we are freezing out the state of the 16 clock signals, and from the state we can calculate the time from the last rising edge to the start occurrence. And the curse measurement is done by the counter, which is shown here. It's simply counting the rising edges of our clock signal, and at the end we have a similar time interpolation as at the beginning. And from calculating the difference from start and stop and divided by 16 times the counter value, we can calculate the time of flight. The in-pixel counter and the counter and the start interpolator are in pixel, and since all the TDCs are stopped globally by an external stop signal, we only use one stop interpolator in global level. So this is our measurement setup. So we have a white paper target and a measured ambient light intensity of about 90 kilolux at this day. And we measure the distance from 2 to 20 meters in steps of 2 meters. And for the illumination, we use a laser diode with 75 watt peak power. It's working at 905 nanometers wavelength, and the pulses have a width of 25 nanometers. We are using a lens with 12.5 millimeter focal length, resulting in a field of view of 0.46 times 36.8 degree. So in this slide, I want to show how the coincidence affects the photon detection. So here, this is the histogram for different coincidence depths from 1 to 4. This is just the raw data which we get from the sensor, and this is a filtered version, just a simple mean filter to make it better visible for you. So we can see if we have no coincidence, so detect or stop our TDC with the first photon, which is impinging, the background light is very high. So therefore, we are just detecting ambient photons, and we cannot measure our pulse, which is here about 330, at pin 330. If we now increase our coincidence depth, so we now need 2 photons to stop our TDC, we can see we can reduce the rate of events, and therefore the ambient light is less, and it's also possible to detect our pulse. Even not very good, but it's possible. And if we increase our depth of the coincidence even more, then the ambient light is reduced more, and the pulse is now clearly visible. And for the measurement in the next slide, we're simply detecting the peak of our histogram, and therefore we can detect it now in the depth of 3. And if we go to 4, the rate is increased very hard, and we cannot measure anything, so only a few events are detected. So this is now the measurement for the 4 different coincidence steps from 1 to 4 over distance from 2 to 20 meters. And we can here see if we have a low coincidence step, so 1 or 2, then we are only detecting the background light, and our peak is always, as we have seen in the previous slide, at 0, and therefore we get a mean value of 0. And okay, our standard deviation is also 0, but at the wrong position. If we use a too high coincidence step, 4 in this example, the few pulses which are occurring are distributed more or less equally above our whole measurement range, and therefore the mean value is about half the range, which is in our case about 100 meters. And as we have seen in the previous slide, for a depth of 3, we can achieve the almost good measurement, or the best measurement for this depth, and can measure up to about 14 to 15 meters. This is another measurement, also the 4 different coincidence steps, and it's the success probability, which means the probability to measure the distance with a given deviation from the true value. And this is plotted over the aperture area, which in principle means the intensity of the light which impinging the sensor. So we can see if we use bigger aperture, which means more light is coming on the sensor, we need a higher coincidence step to reduce the ambient light and enable a measurement. And for the future, or which we are currently working on, the idea is, since we can use our sensor also in counting mode to measure the ambient light, we will use the measurement of the ambient light to automatically adjust the coincidence to the given conditions. So summary, we have designed a 80 pixel line sensor in 0.35 micrometer CMOS technology and use a parallel TDC for all the pixels with a resolution of 312 picoseconds and a full-scale range of 1.28 microseconds. We have adjustable photon coincidence detection to adjust to different levels of intensity, background intensity. And the plan is, or we are currently working on the automatic adjustment of the coincidence to increase the dynamic range of the measurable target reflection. Okay, thank you.